All right, so today we're going to talk about convergence and divergence of series. So let's say you have a series that now is of the form an starting at 1 going out to infinity, and you want to determine whether it converges or diverges. Well, firstly, we're going to do an easy test just to test when this diverges. So we're going to talk about a divergence test. So this series diverges if the limit as n goes to infinity of an is not equal to 0. Okay, but notice how I wrote it. So if the limit is not 0, this one already diverges. Um, but that does not mean what it does not mean is that, and I'm gonna put it in red because that's not true. If limit, so doing a negation, oops, not xn, doing the negation of this. So as limit as n goes to infinity of an equal to 0, then sum from n equals 1 to infinity of an converges. And so the negation of this implies the negation of that. Well, that's not true. So I'm gonna, to make it be, this statement still hold, this is not true. So this statement is not true. So this test is going to be called a divergence test. So this is a quick test just to determine if a series diverges. So for example, I'm going to give you right now a non-example, if you will. I'm going to give you an example of a series I equals 1 to, let's do n, sorry. N equals 1 to infinity. So an infinite series that diverges. So this one, for example, is an example of one that diverges. We're going to determine this, we're going to prove this in a minute. But take my word for this one that this diverges while the limit as n goes to infinity of 1 over n is still 0. So you see, I can say that the limit is 0, and that doesn't imply necessarily that my series converges. Now, in contrast, so to tell you that both things can happen, so if I have the, uh, well, that one is interesting, but this one we know it converges, and what it converges to is converges to pi squared over 6. So here this one converges. And while the terms of the series rather, or the sequence of summands actually converges to 0. So you see, when you have convergence to 0, you can have either convergence or divergence when the sequence of terms converges to 0. The series can't do anything. You don't really know. So, as I said, the only thing you can do is if the limit is not 0, then you know it diverges. So, let's go ahead and do a few examples. So, simple examples for this. So you can do, for example, determine whether the sum of something like I equals, why do I do I? N equals, well, it's because it's more common to do I, but when you're doing more discrete stuff. Anyways, I tend to do sums from I equals 1 to n in my research all the time, so that's why I'm more likely to put an I than an n. Oh well, what can you do? So whether this series converges or diverges. So what do you do? Well, you look at it and say, these terms look like are not going to go down to 0. So you compute the limit. And you say, oh, this is a rational expression on n with equal degrees 1 and 1. So the limit is just the ratio of the coefficients. You can also multiply times 1 over n on both sides and do all that jazz. But we'll leave it at that. This limit is equal to 1/2, which happens to not be 0. Therefore, the series diverges. Let's call it, you know what? Let's write it out. I was going to be lazy. Let's not do that. Diverges. I barely fit it there. All right. Okay, so let's do one more of these. So for example, n equals 1 to infinity of the sine of n pi over 2, for example. You could do that. You could just do sine of n. Doesn't matter. Anyway, this is a fun one because, for example, if you start evaluating it, when n is equal to 1, you get sine of pi over 2, you get 1. Then if you get n equals to 2 is sine of pi, which is going to be 0. When n is 3, you get sine of 3 pi over 2, which is going to be negative 1. Then when n is over 3, so 4, you're going to have 4 over 2, so 2 pi, which gives you a 0. And then the series just starts doing this. And you keep going. So you do 1 plus negative 1. So capital S1 is going to be 1. Capital S2 is going to be 1. Capital S3 is 0. Capital S4 is going to be 0 as well. Capital S, what are we at? 5 is 1. Capital S6, 0. Capital S, what was it? 7? I gotta count. Anyway, so that one is going to give you 0. So you had 1, 1, 0. And you continue like that. And you notice that the partial sums are just going to be going either at 0 or 1. And so this one is kind of interesting because, well, firstly it's going to diverge. Why? Simply because limit as n goes to infinity of sine over n pi over 2 is not equal to 0. Because the sine itself is going to be oscillating between 0, 1, 0, negative 1, and so forth and so on. So it doesn't stabilize down to 0. It just, the limit is undefined, therefore not equal to 0. With that, that's sufficient to talk about the sum from n equals 1 to infinity of sine of n pi over 2, say that this diverges. But this one, this, for example, let's talk for a minute, and this is gonna be beyond this test for divergence, but I just will get off on a tangent, and I'm gonna then after that I'm gonna finish the video. So I'm gonna do this just a single video for the divergence test. Anyways, so let's talk about one interesting not I insist on I. Oh well. It's okay. There's nothing wrong with I. It's just that in this course we're used to using an n there, so it's okay. All right. So anyway, so let's add a few. So when n is equal to 1, you get negative 1. When n is equal to 2, you get plus 1. When n is equal to 3, minus 1, plus 1, and so forth and so on. So this one is interesting because you look at S1 is going to be negative 1. S2 is going to be 0. S3 is going to be 1. See, no, negative 1, 0, negative 1 rather. And you're going to continue like that. But what happens is you can always start rewriting this sum a little bit different. So it's going to be alternating. Obviously, it's not going to converge. But you could say, what if it does? What if it did? Let's call this S. And what you could do is say, well, this term right here is just going to be negative s. You see, you multiply each term by negative and you get the same. And since it goes out to infinity, you could say that's negative s. So you get that s equals negative 1 minus s. And then you can add it and you get s on both sides, and you get 2s is equal to negative 1. And then s would add up to negative 1/2. And would you believe me if I tell you that that adds to negative 1/2? How could it? It's going to be between 0, negative 1, negative 1, 0. But so where is the issue? Well, the issue is I am assuming that this converges, and therefore I can reorganize the sum and get a number. And that is kind of the idea of problems of summability. Can you add them in different order to get different things? And so there are methods of summability, and people study these kinds of questions as well. All right, so, but of course you could have also just moved a little bit further. And how can we make it add something else? Well, we could have added them grouped them in this order. So you start with 0, then you add 0, and you can do just the even. So S2, S4, and rewrite this series in terms of the sums of negative 1 plus 1, negative 1 plus 1, and 1 plus 1, and make them all zeros. And then you can say that this converges to 0 or is equal to 0. So it really does depend on what order you add it. But again, since this is not converging to a number, because the limit as negative 1 to the n as n goes to infinity does not equal 0, then it doesn't converge. So our conversation about saying that this is equal to s or negative s, well, it just doesn't make much sense. Of course, it does raise questions of summability, and then there's things like Cesaro summability and other types of summabilities that arise from these kind of ideas. Nonetheless, for us, if we were asked about the convergence of this one in particular, we say that the limit, this whole conversation was just kind of a little bit, to give you a little bit of an idea where other areas of mathematics are born. So here is not equal to 0 because the limit is oscillating between 1 and negative 1, or the terms are oscillating between negative 1 and 1, so the limit is not equal to 0. Therefore, you have that series diverges. Now, if I would have a limit that gives me 0, please, please, please do not write that it converges. That is not sufficient. That is a necessary condition, but it is not a sufficient condition. So if I had, for example, the sum of 1 over n, if that appears in your exam, n equals 1 to infinity, and you calculate the limit as n goes to infinity, and you find that that is equal to 0, well, you do not say that that diverges. You just do like that little, what is that? It's actually happy, right? Something like that. You don't know. So at that point, we have to do other tests. And that's exactly what we're going to do in the next video. We're going to start with the integral test. This is a perfect example of one that you can compute with the integral test. I'll see you in the next video where we do the integral test.